The simplest way to define an inner product of two vectors from a finite dimensional vector space over R is this. First, you take a basis, b1 to bn, just any arbitrary basis would do, and keep it fixed. Now take the two vectors u and v, of which you want to take the inner product. Express both the vectors as linear combinations of that basis. So you take two tuples of coefficients x1, x2, etc. to xn for u and y1 to yn for v. Now take the usual dot product of these two tuples. Let us demonstrate this with an example. Suppose as our vector space we take the space of all polynomials over R of degree less than or equal to 2. And as the basis we take 1, x and x squared. Next we take two vectors, that is two polynomials. The first one is 2 minus 3x plus 5x squared and the second one is 5 plus x squared. When I expand this polynomial as a linear combination of this basis, I get 2 times 1 plus minus 3 times x plus 5 times x squared. And when I expand this polynomial, I get 5 times 1 plus 0x plus 1 times x squared. So the inner product becomes 2 times 5 plus minus 3 times 0 plus 5 times 1. And that equals 15. Now, if I change the basis to 1, then 1 plus x and x squared, this inner product will change. Now the first polynomial will expand into this. So the coefficients are 5, minus 3 and 5. The second polynomial will expand to this 5, 0 and 1. So now the inner product will be 5 times 5 plus minus 3 times 0 plus 5 times 1, which is 30. Thus, an inner product is basically a function that combines two vectors from V into a single real number. Now, the way we define inner product by first fixing a basis shows that the particular inner product depends on the arbitrary basis that you have fixed at first. So, ideally, we should write it as inner product with a subscript of B, the basis. The presence of this B is irritating because when we want to state any result in terms of inner products, we want to know whether the property really depends on the vectors chosen or on this arbitrary basis. Now that is our problem 1, that the arbitrarily chosen basis might play a role which we do not want it to play. The second problem is with infinite dimensional vector spaces, because there we cannot just fix a basis and express everything as a tuple, because that so-called tuple will now become infinite in size, so simply adding them or multiplying it is not very easily done. In order to avoid these two problems, we take a different approach. We start by making a list. We make a list of all the properties of inner product that we use for proving different useful theorems. Now that's a long list. Now in this list there are various properties which are actually consequences of other properties already in the list. We throw those consequent properties away. In other words, we are trying to make a minimal list which contains the entire essence of all these properties. In the sense, give me any property here, it is either in the minimal list or maybe proved from the minimal list, but this is the shortest. You cannot prove this from these or this from those. Now of course, there is no such unique minimal list. I can come up with one list, you can come up with another. In that case, your list and my list will be equivalent, in the sense everything in your list can be proved from results from my list, and similarly everything from my list may be proved from the things in your list. Now there is one universally agreed upon such minimal list. The first item there is this, that for all x or all vectors, inner product of x with itself must be greater than or equal to 0, and it will be equal to 0 if and only if the vector is the 0 vector. The second item in the list is symmetry. For all x, y, you can put them in any order, it doesn't matter. The third property is kind of distributivity or linearity in the first argument, which says this: for all AB scalars, for all UVW vectors, if the first one is split, then the entire inner product gets split. Thanks to the second property, you can do the same thing with the second argument as well. Now we can take this as our definition. So here is the second definition of inner product. By an inner product, we shall understand any function from V cross V to R that satisfy these three axioms. In the next video, we shall see how these two definitions interact.